Our second video from chapter 11 is centered around palladium with a little bit of boron sprinkled in. Because in 11.4 here, we're going to talk about another tool to form carbon-carbon bonds, and that's in using palladium-catalyzed coupling. And there's two key reactions here that are somewhat similar to one another, the Suzuki reaction and the Heck reaction. Okay, two named famous reactions for forming carbon-carbon bonds that you'll definitely want to know from chapter 11. That's Suzuki reaction and the Heck reaction. Both are substitution reactions catalyzed by palladium. Okay, and what they do is they take either a vinylic halide or an aryl halide and replace the halogen, right, with something containing carbon. Notice the halogen, bromide or iodide on this side, is replaced by R. So we're forming another alkyl group, right? Putting another carbon-containing group on there in place of the halogen. But the key thing for both of these reactions specifically is they do have to originate from vinylic or aryl halides. Okay, we can't just use any type of alkyl bromide for the Suzuki or the Heck reaction. So how do they work? Okay. We've got palladium as our catalyst that's coordinated to a number of possible ligands, right? Recall from Gen Chem 2, right? What a ligand is, forming a coordinate covalent bond with palladium. And changing the ligands changes these mechanisms a little bit, but for the general scope of the chapter, we're just going to think about general ligands on palladium, okay? And our active catalyst in these two reactions has two ligands. And a common ligand that you see for palladium is triphenylphosphine. Yep. Both Suzuki and Heck undergo a catalytic cycle, where palladium both helps break bonds in the reactants and form new bonds in the final product. That's that new carbon-carbon bond. Yep. And the first step in both of them, the Suzuki and the Heck reaction, after we've generated the catalyst, is insertion of palladium between carbon and the halogen in the aryl or vinylic halide that we've started with. That forms an organopalladium complex. But the reason we have to use vinylic or aryl halides is we have to be on the lookout for beta hydrogens when we're working with organopalladiums. Because if you have beta hydrogens, then you have the risk of undergoing an elimination. Okay. So as I mentioned, the first step is insertion, right? Palladium goes in. That's called an oxidative addition. We'll see that term again here in just a second. Okay. But for all your substituents, specifically your carbon-based substituents, you've got to look out. If there's a beta hydrogen, elimination is going to happen before you have a chance to have any sort of coupling reaction and form that new bond. Right? Notice over here, my alpha carbon, my beta carbon. My beta carbon has hydrogen. Okay, no dice, right? It undergoes what's known as a beta elimination. We've seen that before. It forms an alkene, and I haven't formed a new CC bond. Right? So you can't have beta hydrogens with your organopalladiums. Make sure you're looking out for that. Vinylic and aryl halides only. So as long as we meet those criteria, right, these reactions are famous for a reason. Right? They can work around a variety of other functional groups as long as there's no beta hydrogen present. They're stereospecific, right? Meaning just like in video 1, our double bond configuration is retained. If it started out cis, it finishes cis. Trans stays trans. And they're super efficient catalysts and reactions, right? We just use 1/10% of a catalyst, right? Produce 80 to 98% yield. Okay, so incredible synthetic utility. So let's look at both of them, Suzuki and then Heck. This is the general scheme of the Suzuki reaction. Okay? Suzuki takes vinylic or aryl halide and uses an organoboron compound in basic solution. Notice the hydroxide over here with our palladium catalyst. And that takes the alkyl group that was attached to boron with the group from our vinylic or aryl halides, connects them together. Right? So there's a ton of possibilities in terms of the reactions. Right? Your organoboron compound over here, right, can have an alkyl group, it can have an alkenyl group, it can have an aryl group. Any one of them, just take the group from boron, right, put it in place of the halide, shown on the left there in that pink-purple color, and then boom, that's your product. Incredibly simple to meet. right? It just has to be a vinylic or an aryl halide to start, plus an organoboron, palladium catalyst, basic solution, new bond, bam, done. Keeping in mind that stereochem is retained, right? This was trans, so it stays trans. Yep. How? We'll look at the mechanisms next. The challenge from chapter 11, the primary goal, right, is know how to predict the products. But if you're wondering how, we'll look at the mechanism on this slide, keeping in mind what I mentioned before. If you change the ligands on palladium, it can change the mechanism a little bit. Okay. I alluded to it just a few minutes ago. Palladium with 2 ligands is the active catalyst, right? But that's super reactive and unstable. So it has to be generated in situ, right in the test tube by 2 successive ligand dissociation reactions. We start with 4, we drop 2 of them, got our active catalyst, and then we're in business. Okay. Then first step in both of them, right? Palladium gets inserted in this bond. Okay, so notice we went from R to Br to now R, palladium, Br. After that, hydroxide comes in, right, and displaces our halide, in this case bromide. Okay, so hydroxide comes in, switches it out. Okay. Then our R group from our organoboron is transferred from boron to palladium, and hydroxide gets transferred from palladium to boron. So effectively, they're just swapping their partners. Okay, so that gives me palladium with both alkyl groups. Okay, and then that palladium is eliminated, and that's what makes our new CC bond, and in the same time regenerates our catalyst, so we can do it all over again. Okay. The fourth step down here, switching those ligands, that's a transmetallation. We talked about that in video 1. Okay. These 2 other terms are key ideas to have for this chapter. Okay. When palladium gets inserted into that bond, that's an oxidative addition. And when it gets eliminated and we form the new CC bond, that's known as a reductive elimination. Know these 2 terms from chapter 11. Okay? Oxidative addition is when we insert a metal between 2 atoms. And it's called that because the metal gets oxidized and it adds extra ligands. Reductive elimination. We eliminate groups and the metal gets reduced. Simple as that. Make sure you know those terms. Okay? The other question, where do the organoboron compounds come from? Yeah. Basically, you just take a terminal alkene or an alkyne and you do a hydroboration, but then you don't do the oxidation. Okay? And then you get your organoboron compound. You can also prepare it from an organolithium. Okay? Take an organolithium, react it with a borate, okay? Do a ligand exchange there, and bam, you've got your Aryl-Organoboron compound. So that's everything Suzuki. How about Heck? Heck reaction is similar to the Suzuki reaction. We have to start, as I mentioned at the beginning of the video, with a vinylic or an aryl halide, but now we're bonding specifically to an alkene. Still a substitution reaction. Okay? Our R group over here is replacing hydrogen, specifically a vinylic hydrogen. Right? So it's a substitution reaction. We still keep the configuration of our double bond. Trans stays trans, cis stays cis. So let's look at a couple examples of these Suzuki reactions. Okay, vinylic or aryl halide, okay, an alkene, palladium catalyst, triethylamine, forms a new carbon-carbon bond. We're still just putting these guys in place of the halogen. Okay, specifically now joining 2 sp2 carbons together. So what's this mechanism look like? Okay. Again, similar to Suzuki, a couple of extra steps though, specifically with what's going down at the bottom. And I have them listed on the following 2 slides. Right? To put it succinctly, we generate our catalyst, right? Just like before, we undergo an oxidative addition. Okay? Then we do what's called a ligand substitution down here. Right? We've taken now this alkene and swapped it for one of our original ligands on palladium. So notice that ligand has left. Yeah. Then our R group that's on palladium here, because keep in mind it's an organometallic, is a nucleophile. So it's going to add to the sp2 carbon of the alkene, right? And that's a concerted syn addition. Then this green arrow down at the bottom is showing rotation about our bond, okay, to get the proper configuration for the final step. And I failed to mention right here, these are also, right, notice the bond switches. We go from our alkyl group attacking there, and these pi electrons come back to form a bond to palladium. Then we rotate. Then we have a hydride that gets transferred to palladium, right? Once we have the proper rotation down there. I keep having this thing pop up in the way. But you've got a hydride, right? We rotate about so that the hydride is closer to palladium. Hydride gets transferred to palladium, and then electrons form our pi bond. Then we have a concerted syn elimination. Yep. Then we have, again, another ligand substitution that knocks off our product, and then a reductive elimination to regenerate our catalyst. Okay. That produces HBr as a byproduct of the reductive elimination, which is picked up by the triethylamine, driving that reaction forward. All of those steps are also listed out on these following slides. One last consideration for the Heck reaction. What do we want to do to get this reaction to have as high yield as possible? Okay. It works best if our alkene is symmetrical, okay, because then you naturally have higher yields. Right? But if not, you want to make one of your sp2 carbons sterically hindered. Okay. Now, we don't want to go to using internal alkynes. Right, those guys usually aren't used. Internal alkynes before. Internal alkenes. We're usually not using internal alkenes because they have too much steric hindrance, okay, and they're less reactive overall. Okay? But if we have a terminal alkene and one of these guys is sterically hindered, it helps in that nucleophilic addition, right, getting the high yield of the correct product. Lastly, right, if we put an electron withdrawing group near our alkene, that makes it a better electrophile and helps again with the nucleophilic step, which is what's shown. One more slide going on right down here. Okay. So 2 important mechanisms to know for in reactions, being able to predict the products for section 11.4. Suzuki reaction, Heck reaction, know what to use and what they make. And we'll finish chapter 11 by talking about alkene metathesis in the last video.